Welcome to our channel. Have you ever heard the hypothesis that the entire universe we live in might be nothing more than a three-dimensional projection, like an image created from information stored on a flat surface? It may sound like a concept straight out of science fiction, but this is exactly what the holographic principle proposes, one of the most fascinating theories in modern physics. To understand it more clearly, let's delve deeper through surprising stories and historical examples. The holographic principle is one of the most intriguing and challenging ideas in modern theoretical physics. First proposed in the 1990s by theoretical physicist Gerard Hooft and later expanded by Leonard Susskind, this principle raises a major question about how we perceive the universe. Where did this idea originate? To comprehend it, we need to go back to the study of one of the universe's most mysterious phenomena, black holes. Black holes are regions of space with such intense gravitational forces that nothing can escape, not even light. However, during the 1970s, physicist Stephen Hawking introduced a controversial hypothesis. Information might be lost when matter falls into a black hole. According to quantum theory, information cannot be completely destroyed, which created a significant conflict with the laws of physics. This issue became known as the black hole information paradox. These contradictions prompted Gerard Hooft and Leonard Susskind to hypothesize that information does not actually disappear, but can be encoded on the surface of a black hole. The way this information is stored can be likened to the principle of a hologram, where information about a three-dimensional image is encoded and stored on a two-dimensional surface. This led to the idea that our entire universe could be a three-dimensional projection of information stored on a surface. To visualize this more easily, imagine watching a 3D movie. The images on the screen appear to have depth and space, but in reality, they are just projections from a flat surface. According to the holographic principle, it is possible that the three-dimensional space we live in is also a projection from another surface beyond our observational reach. This idea is not merely theoretical, but has been supported by various studies and physical models. It is closely related to string theory and loop quantum gravity fields that strive to provide a unified explanation between quantum mechanics and Einstein's general theory of relativity. Over the past few decades, the holographic principle has become a central idea in explaining the universe and the formation of space-time. Another intriguing aspect is that this principle can apply not only to black holes, but potentially to the entire universe. This leads to the hypothesis that all objects, space, and even time may only be projections from a two-dimensional surface. Although this idea remains controversial, it has opened new doors for research into quantum phenomena and cosmology. So, what would happen if the holographic principle is true? This is not merely a theoretical question, but a major challenge to our perception of reality. If everything is a projection, then the reality we see might only be a complex illusion of a vast information encoding system. This raises fascinating questions. Is human consciousness a part of this projection? Or can we reach the encoded surface of information and alter it? The holographic principle is not just a theoretical idea, but a major challenge for scientists as they strive to find evidence to support it. In the next section, we will delve deeper into real-world experiments and methods that scientists have used and are using to verify this idea. The holographic principle is a groundbreaking theoretical concept, but to test and transform it into a practical theory, scientists must rely on real experiments. One of the most significant experiments related to this principle was conducted at the Laser Interferometer Gravitational Wave Observatory, LIGO. Initially, LIGO was built with the aim of detecting gravitational waves, ripples in space-time, caused by massive cosmic events such as black hole collisions or supernova. However, during its operation, scientists at LIGO detected small fluctuations in data that could not be easily explained. Some researchers suggested that these fluctuations might indicate the presence of a quantum graininess in space-time, a hint that space-time might not be a continuous entity, but rather a quantum combination of particles. This aligns with the idea that the universe could be a quantum encoding, supporting the holographic principle. Nevertheless, testing this idea is not simple. The fluctuations observed by LIGO still need to be rigorously verified and examined to rule out other causes. But this discovery has sparked a wave of discussion within the physics community, with differing opinions on whether this could be evidence of a truly quantum-structured spacetime. In addition to LIGO, other experiments have focused on testing hypotheses related to the holographic principle. An example is the Fermilab holometer, a highly sensitive device designed to detect micro-vibrations of space-time. The holometer operates with extreme precision, measuring fluctuations at the subatomic level. If space-time is truly quantized, as the holographic principle suggests, the holometer could detect even the smallest changes in its structure. Although conclusive results have yet to be produced from these experiments, they provide hope that in the future, science may be able to verify complex theories like the holographic principle. One major challenge for scientists when testing this theory lies in the complexity of quantum phenomena and how they interact with space-time. The quantum world often defies familiar laws, making measurement and verification far more challenging. The difficulty of verifying the holographic principle also stems from its inherent nature. The principle suggests that all information in the universe may be encoded on a two-dimensional surface, meaning that phenomena we observe in three-dimensional space are merely manifestations of information from that surface. This can be compared to seeing the image of an object on a computer screen. What we see has depth and detail, but in reality, it is just a collection of data points on a two-dimensional surface. Another issue related to testing the holographic principle is the role of dark energy and dark matter. These two components make up the majority of the universe and have a profound effect on the structure of space-time. However, their nature remains largely unknown, complicating any attempts to verify theories related to space and the universe. Additionally, debates within the scientific community cannot be overlooked. Some physicists argue that focusing on testing the holographic principle may be a waste of resources due to the lack of clear empirical evidence. Others believe that exploring bold theories like this is necessary to expand our understanding of the true nature of the universe. Overall, the journey to test and verify the holographic principle is a challenging yet fascinating one. It requires precision, advanced technology, perseverance, and a willingness to confront questions that may not have immediate answers. These efforts bring us closer to understanding the true nature of reality, whether everything we see and perceive is real or merely a projection of some invisible information. The holographic principle could be the key to unlocking the deepest secrets of the universe and the nature of reality. Whether you believe it or not, it is certain to make us reflect on the truth behind what we see and experience. What do you think about this theory? Please share your thoughts in the comments section. Thank you for watching, and see you in the next video.